While staying in Nicaragua, the pirates have made a new friend, Senor Ortega. He's the owner of a famous cocoa plantation. Today, he is showing them how he grows and harvests his crops. Recently, he received a shipment of fertilizer, but parts of the labels were washed away at sea. Being a proud cocoa producer, Senor Ortega isn't ready to put just any mixture of fertilizer on his beloved crops. He needs to know the exact composition of what he's feeding his plants. Of course, Long Jane Silver is worried about her new friend. She does love chocolate, after all. Luckily, she knows what to do. They can use gravimetric analysis to determine the percentage composition of the fertilizer. If you recall from the previous lesson, gravimetric analysis is a quantitative technique that is used to determine the mass of one or more substances in a mixture. In general, it involves 4 main steps. To begin, we measure the total mass of the mixture. Next, we separate the components of the mixture using one or more appropriate separation techniques. If you would like to revise the various methods of separating mixtures, please see our earlier videos on separation techniques. Then, we measure the mass of each component of the mixture. To finish, we calculate the percentage composition by weight of each individual component. In this lesson, we will perform a practical investigation or experiment which involves gravimetric analysis. In the next lesson, we will assess the accuracy, reliability, and validity of this practical investigation. Let's see what Senor Ortega and Long Jane Silver have discovered so far. The fertilizer contains a heterogeneous mixture of wood chips, potassium sulfate, and soil. Unfortunately, the label doesn't tell them much more than that. Remember, a heterogeneous mixture is a mixture that has variable composition and properties, so the components are unevenly combined. Senor Ortega insists on finding out the exact composition of the fertilizer mixture. In other words, his aim is to determine the percentage composition by weight of the fertilizer. This can be achieved by performing gravimetric analysis. As we mentioned earlier, the first step of gravimetric analysis is to measure the total mass of the mixture. Senor Ortega places a 150 milliliter beaker on an electronic mass balance. He waits for the reading to stabilise and tears the balance. Then he uses a metal spatula to place a sample of the fertilizer into the beaker and record its mass. Hold on, Long Jane Silver brings out another 3 beakers. She informs Senor Ortega that they might need to transfer the soil into a different container and that each beaker weighs a different amount. To avoid confusion later on, they label the beakers A, B, C, and D and record the mass of each beaker. To be certain about their results, they repeat the first step. The fertilizer sample is in beaker A, which has a mass of 66.18 grams. The total mass of the beaker and the fertilizer is 96.25 grams. Subtracting these gives the mass of the fertilizer, which is 30.07 grams. Now that the first step of gravimetric analysis is complete, do you know what comes next? We need to separate the components of the mixture using one or more separation techniques. In this case, the fertilizer is a heterogeneous mixture of wood chips, potassium sulfate, and soil. But how will Long Jane Silver and Senor Ortega go about separating the 3 components? They will need to plan each step before they begin the next phase of their experiment. If you recall, pure substances retain their distinct physical properties when combined. Hence, we should look for differences between the physical properties of each component in the mixture. Can you identify any differences between wood chips, potassium sulfate, and soil? Firstly, the wood chips are larger in size than the soil particles and potassium sulfate crystals. Therefore, the wood chips can be separated using the physical property of particle size. Do you recall a separation technique that relies on differences in particle size? In this case, sieving is an appropriate separation technique for isolating the wood chips. Meanwhile, potassium sulfate is soluble in water, whereas wood chips and soil are not. Thus, the potassium sulfate can be extracted using the physical property of solubility. Can you identify any separation techniques that depend on differences in solubility? Water can be added to the mixture to dissolve the potassium sulfate. Then, the insoluble components can be removed using filtration, leaving potassium sulfate solution as the filtrate. Since sieving works best with a mixture of solids, it should be performed before forming a solution. Now that they have developed a general approach for separating the components of the mixture, they can finalise their experimental method. In this process, they should also consider the third step of gravimetric analysis, measuring the mass of each component of the mixture. Pause the video here if you would like to write the experimental method by yourself. Otherwise, continue watching and we'll go through the method step by step. Firstly, Long Jane Silver sieves the fertiliser sample. She also places beaker B under the sieve. This way, the wood chips remain in the sieve while the potassium sulfate and soil collect in beaker B. Once the wood chips have been isolated, she can transfer them into an empty beaker. She can measure the total mass of the beaker and the wood chips, then calculate the mass of the wood chips. Returning to the second beaker, it contains a heterogeneous mixture of two solids, soil and potassium sulfate. Since potassium sulfate is soluble in water and soil is not, they can be separated by forming a solution. So, Senor Ortega adds 100 millilitres of distilled water to the mixture and stirs with a glass rod to dissolve the potassium sulfate. This forms a heterogeneous mixture of potassium sulfate solution and insoluble soil. Next, Long Jane Silver measures the mass of one piece of filter paper. You'll see why this is important later on. Senor Ortega pours the mixture through a filtration setup. The filter paper collects the insoluble residue, which is soil, while allowing the filtrate, or potassium sulfate solution, to collect in the fourth beaker. Since the soil is damp, Senor Ortega will need to dry it out before proceeding further. If he weighs the sample now, the mass of the absorbed water will make his results inaccurate. Consequently, he places the wet filter paper and soil onto a watch glass and leaves it to dry overnight. Afterwards, he measures the total mass of the filter paper and soil residue. Thankfully, Long Jane Silver measured the mass of the filter paper earlier. By subtracting these values, Senor Ortega determines the mass of the soil. At this point, Long Jane Silver returns to the filtrate, which is a homogeneous mixture of potassium sulfate and water. Since potassium sulfate has a much higher boiling point than water, she can isolate the crystals by evaporation. She measures the mass of an empty evaporating basin, then pours the filtrate into the basin and allows the water to evaporate. To speed up the process, she heats the solution with a Bunsen burner. Once all the water has evaporated, she leaves the basin to cool. She measures the total mass of the evaporating basin and potassium sulfate crystals and calculates the mass of the pure potassium sulfate. Finally, Long Jane Silver and Senor Ortega have finished separating the mixture and taking measurements. Pause the video here if you would like to read through the first half of their experimental method. And pause here to read the second half of their method. Now that they've measured the weight of each component in the fertiliser, they are ready for the final step of gravimetric analysis. This involves calculating the percentage by weight of each individual component. They begin by calculating the percentage of wood chips in the fertiliser mixture. Long Jane Silver writes down the relevant data from her experiment. Then she writes down the formula for percentage composition. In this case, the mass of the substance is the mass of the wood chips, while the mass of the mixture is the total mass of the fertiliser sample. She substitutes the values into the formula, making sure that both masses are written in the same units, grams. After calculating the answer, she finds that the percentage by weight of wood chips in the sample of fertiliser is 37.4127%. Since the mass of wood chips and the mass of the fertiliser sample are both known to 4 significant figures, we should round our answer to 4 significant figures. Thus, the percentage by weight of wood chips is 37.41%. She follows this process again to determine the percentage by weight of soil in the mixture, which is 60.59%. Similarly, she finds the percentage by weight of potassium sulfate in the mixture is 17.1%. Finally, she can tell Senor Ortega that the percentage composition by weight of the fertiliser is 37.41% wood chips, 60.59% soil, and 17.1% potassium sulfate. This is exactly what he ordered. He is so relieved that he gives the pirates another barrel of cocoa beans. They'll be drinking hot chocolate for months. Long Jane Silver looks more carefully at their results. Hold on, something's not right. She calculates the total of each column in the table and finds that the numbers don't add up. The mass of all the components of the fertiliser is greater than the mass of the fertiliser, and their percentage compositions add to more than 100%. Did they make a calculation error, or did they perform the experiment incorrectly? In the next lesson, Gravimetric Analysis 2, we'll explain these inconsistencies and discuss other potential pitfalls of this experiment. Let's revise what we've covered in this lesson. You should be able to apply your knowledge of separation techniques and gravimetric analysis to determine the percentage composition by weight of homogeneous and heterogeneous mixtures. Gravimetric analysis is a quantitative technique that is used to determine the mass of one or more substances in a mixture. It involves 4 main steps. Firstly, we measure the total mass of the mixture. Secondly, we separate the components of the mixture using one or more appropriate separation techniques. Thirdly, we measure the mass of each component of the mixture. Finally, we calculate the percentage composition by weight of each individual component. To calculate the percentage composition by weight of a mixture, we use the following formula.